So the lesson outcome, you must know what is the period, group and block, which as PDF, and specify the position of metals, metalloid, and where is the non-metal is located in the periodic table. Explain the variation of atomic, ionic radiant, and also isoelectronic radiant. Define first and second ionization energy, and then define electron affinity and electronegativity. And also you must be able to explain the variation of electronegativity of the. Okay, so Dmitry is the first chemist that developed periodic table. So he came from Russia, and also Lothar Meyer came from Germany. Okay, alright, so they combine and publish the periodic table arrangement of the element based on the increasing of atomic number. So this is how the periodic table looks like on the first time it has been developed, okay, back in 1869. Right, so this is nowadays periodic table has been regenerated and rearranged again according to the increasing of atomic number. So we have metal, metalloid, and also non-metal groups. So these are metalloid, one that with gray color, and then on the right side are all non-metals. Right, starting from group 4A, and then 5A, 6A, 7A, and noble gas, and then we have also we have metal on the left side. So down here we have lanthanide and lanthanide group down here. Right. Okay. Right. Okay. Next, classification. All of us know that group 1A is known as alkali metal, group 2A is alkaline, and group non-metals located of group halogen at 7A, noble gas at 8A. Okay, metalloid possess both metallic and non-metallic properties, such as this one, like boron, silicon, gallium, arsenic. Okay, and then we have so on. Okay, part of the periodic table, so we must know what is group. Group means it has different column of the element, normally on the vertical lines. Okay, so group consists of elements that have the same number of electron valence, which is the outermost shell is the same. The total group of 18 is 1 to group 18. Alright, so this one. Okay, when we draw the electron configuration, the ended last number must be similar. So they are coming from the same group. Okay. And they have the similar reactivity within the group as well. So for example, lithium, sodium, and potassium, they are very reactive. Okay, they are very reactive. They are alkali metals, so they are very reactive. Same goes to the group 17 or group 7A from halogen gas, so they have the same properties. Yeah. Okay. So period is something that has horizontal bars. Alright, they have the similar. Okay, so for example, this one. Okay, from period number 2. So when you do electron configuration, they have similar electron valence shell. Right, same goes to period number 5, for example. Okay. Okay, so classification according to valence shell of electron configuration. Normally for S block element, we have NS1 and NS2 because S only have 2 spin, 2 electrons. Okay, for P, we have NS2 and P1 up to NS2 and P5. Alright, noble gas. This is how we fill the noble gas. Okay, because 6 plus 2 is equal to 8. Alright, so for this P block, it could be up to 7. Okay, for D blocks, from 1 to 10. Right, so F block is 1 to 14. Okay. Alright, so we have here, right, for example, this is S group. 1, 2, 3, 4 is indicate the period. Okay, for transition metal, we start with 3D, 4D, 5D, and 6D in this region. For P group, we have 2P, 3P, 4P, 5P, and 6P. Okay, and lanthanide and actinide, we have 4F and 5F. Yeah. So this is all the F transition metals. Right. Okay, so this is how we write for period number 1, 1s. That's it, because S only has 2 electron. For 2s, we're going to have 2p as well. Okay, for 3s, we're going to have 3p. For 4s, we're going to have 3d and 4p. I have explained before in the previous chapter why 4s is lower. For group number 4, 4s, and then we come with 3d because of 3d has the higher number compared to 4, has the lower energy compared to 4p, and then 5s, 5d, 5p, and so on. Okay. So this is for a family elements, the valence electron configuration is the same. Yes, this is how. Okay, for example, you are from level this period, from period number 2, so 2s1 to s2 to s2 to p1 to s2 to p2 to s2 to p3 and so on. Okay, alright, until it fulfill the octet of 2p6. Okay, for period number 3, we have 3s1 up to 3s2, 3p6. So if we fill the octet of s and p, both will give 8, yeah? 8 at the valence electrons. Okay, but we have some exception for helium, which has a field of s orbital. The noble gas has to fill the p orbital. This is for example, Alright, for helium group, not only for helium group, we have another for this one, Alright, so this is how we write condensed electron configuration. I have mentioned in the previous topic as well. Alright, so for example, for period number 2, in order to write the condensed ground state, you have to refer who is the noble gas before the period. Okay, for example, this is period number 2. The noble gas for period number 1 is helium. Helium bring two atomic number. So meaning that this is 2 and then 2s1. So 2 plus 1 is equal to 3 atomic number. So helium to s2, 4. 2 plus 2, 4. So become this one. Alright, so this is how we write condensed. Okay, so now you look at period number 3. Period number 3, who is the noble gas before it? It's neon. Neon number is 10. Okay, atomic number is 10. So you should know how to write it. Write Ne for this period. Then 3s, how many electron remaining? This is 10, so one more remaining for sodium. Okay. Then same goes to, for example, this one, chlorine. Chlorine is 17, so 10, 12, 15. Okay. 12 plus 5 is 17. Okay, so 3p5. So you get it. And E, 3s2, 3p5 as a condensed configuration. Okay. Right, so now determine the block, period block and group for each element with the following configuration. If you look at this one, so this is coming from which period? So I want you to answer this one, simple one. Okay. Right, so look at number 1. Okay, for example, this from period number, the last remaining period is 2. This is from period 3. This is from period 3. This is from period 4. Okay. Right, look at this one. This one, look at this one, not this one. Okay. Alright, so now period 2 and then which block? The M block is block P. Which group? Okay, 2 plus 5, 2 plus 3 is equal to 5. So group 15. Okay, this is group 15. Alright. And then this one. Okay, block P as well. From which group? 6 plus 2 is equal to 8 from group 18. Alright. And then period 3, S block, group 2, because it's only 2 element here. Okay. Right, and then this one, period 4, block D. This is the last block. Okay, the block D, and then come from group 5. Alright. Okay. Alright. Okay, for P block, normally it's group 4, 10 plus the electron valence. That's why you got 15. But this one for D block. Okay, D block, which is a transition metal, you don't have to add 10. So that's why it's become group 5. Okay. Right, for P block, we add, though this is 8, so we add 10 to it. So that's why you got 18. Okay. So now we go with periodic physical properties. Physical properties normally it has according to the atomic size, ionization energy, electron affinity, and also electronegativity. Okay, one by one. Okay, look at one period. For example, we have 1s2 to s1. Okay, 1s2 to s2. This is period 2. Period 2. Be has smaller radius than Li because there is one more electron and the attraction between them is stronger. So we have extra one more electron here compared to here. Alright, so this is the attraction will be higher, will be stronger. The shell get full and tighter around the nucleus. Okay, so it has more energy to attract. Okay, to attract the electrons. So that's why Be become smaller radius. Okay, and then in fact, in order to know either this one is smaller radius or not, look at it has now 2s2. Okay, 2s2 a bit far away from 2s1. Okay, compared from the nucleus. Yeah. So moving down the group, okay, another shell is added. Okay, for example, we have 1s1, 1s2, 2s2, 3s2, 4s2. Okay, so now we have 4 period. Example like helium, lithium, sodium, and potassium like this. Each new shell is further from the nucleus, so an atomic size will be increased. Atomic size, you tengok radius dia memang akan makin besar. Okay, radius size will be bigger by attraction. Okay, atomic size is half of the distance between two nuclei whose adjacent atom. Half T, do you know the formula? So atomic size is determined by two factors, screening effect and also nuclear charge. Look at screening effect. Atomic radius increase downwards in the group. Atomic radius increase because of we got more period added, so that's why the size become bigger. Instead of hydrogen, look at this size, now it's become bigger. But when it's across the period, what will happen? Shielding effect will be remain the same. Okay, shielding effect remains the same, but ZeF number increase across the period from left to right. Okay, so you look at this one. Okay, this is of example of shielding effect. Okay, electron fill up a new shell downwards. The outer electron are shielded from the nucleus by electron in the inner shell. Alright, so mutual repulsion between the different has less tightly. Yes, betul. Alright, so this one for example. Okay, for example, hydrogen now is 1 compared to helium. Francium, francium is 87. 87, the shielding effect is more army now that's protect the nucleus. Okay, we got more orbital, more army that protect the nucleus. So shielding effect will be the same, but ZeF number it will be increased. Yeah. Right. So this is the outer electron where you look at the repulsion. So this is the outer electron that it has repulsion. Repulsion happen between the period and period. Okay, period and period only, but attraction happen between period and nucleus. Okay, repulsion just happen between the period only. Yeah. Alright, as you goes down the group, atomic radius is increased, more shell are added, so repulsion by inner electron. So that's why the effective nuclear charge will be decreased. The outer electron further away from nucleus, correct, so that's why atom size will be increased. But the attractive force due to the inner electron is called as screen effect will be Alright, so now we look at nuclear charge, ZeF. They decrease towards right to left, okay, towards the right across a period. Okay, electron fill up the same shell, cause effective nuclear charge ZeF of the atom increase with pull all the electron closer to the nucleus, thus the electron are more held tightly. Right. So this is relation between ZeF and atomic radius. Atomic radius indirectly related to ZeF number. If ZeF number increase, atomic radius will be decreased. So when we know that atomic increase down the group, so meaning that ZeF will be increased up from bottom to from will be what we call it will be the other way around. So if you have down the group, radius increase, but Z number will be decreased. Okay, so atomic radius across the period, atomic radius will be decreased, but the Z number will be increased. Okay. Alpha is the sigma is the shielding constant, the number of inner shell of the electron. As the distance from nucleus increase, sigma will be increased and Z will be decreased. Radius the distance between nucleus and the electron in the outermost shell of the ion. When the atom lost an electron to form cation, the lost electron no longer contribute to the shielding effect. Thus, electrons are more strongly attracted to the nucleus and radius of the atom gets smaller. That is only happen when you donate an electron or you lost an electron. You don't have any more shielding at the back. Okay, so that's why you are now your attraction becomes stronger. If you have more period, it become lesser, right? So now you have more stronger to the nucleus, radius getting smaller. Okay. Right, so this is size of cation. Can look at size of the cation getting smaller than the corresponding parent atom. Right. So as we goes down to the group, size of atom will be added. So because we have more period, alright. Okay, we got more period. So the atomic, the radius become bigger and bigger and bigger and bigger. Right. And size of atom become bigger as well. Okay. Right, so size of an ion are larger compared to the corresponding parent atom electron, and tend to repel each other, and so the size will be increased. Right, for example, Cl ion have bigger size compared to Cl atom. Yes, this is because of when you have minus, you attract more. Isn't it? So you accepting more electron towards you. When you have more electron towards you, you're adding more period. You're adding more shield. Okay, so that's why your size become bigger. Okay, right. Okay, for cation, you have Na plus, for example. Na plus lesser than Na because you have plus, meaning that you are going to donate. You are going to donate your electron. Once you donate one electron, so basically your size will getting reduced. So that's why you are getting smaller. Alright. So I'll stop here first. We continue after this.